what we're seeing is that the reduced row echelon form for a matrix is really the sort of nicest way to get at the solution set for a system of equations. To see another reason why that is, let's look at this example. Suppose that we had a system of equations and we wrote down its augmented matrix and then did row reduction on that to get this, and we ended up with this for its reduced row echelon form. Remember that since we started with an augmented matrix, this last column is really representing the right-hand side of the equation. So, often we've actually written out the equations that this reduced row echelon form corresponds to, like this. So x1 plus looks like x2. Sorry, that should be x3 plus 3x4 equals minus 2, and then the second equation corresponds to x2 minus x3 minus x4 equals minus 2. And then we've finished solving this by just moving the free variables over to the right. So that would give us x1 is minus 2 minus x3 minus 3x4, and then x2 is minus 2 again, plus x3 plus x4. But if you look at what we did here, and then x3 is x3 and x4 is x4, because these two are free variables, right? So they there's no equation that determines them, they can be anything. But if you look at what we started with and what we're ending up with, these coefficients here, which were the coefficients for x3, they end up with their signs reversed right here. And correspondingly, these two coefficients, these two entries, are really, they show up in our solution as coefficients for x4, but their signs are reversed here and here. And the signs are reversed because we moved them from one side of the equation to the other. So when we write this out as column vectors, what we get is we get a vector with the constants, that is the stuff coming from the right-hand side. So for the non-free variables, right, we have these constant entries here, minus 2 and minus 2. For the free variables, well, there will never be any constant part of the free variable, because the free variables are always going to say, for example, this one just x3 equals x3. There's never going to be some constant in front here, so we'll just add zeros for all the free variables. And then for each free variable, we're going to get a column vector times that free variable, right? So the entry here corresponding to the free variable that I'm writing this term for, we need a 1 here because x3 is supposed to be equal to x3. The other free variables will have a 0 because the equation determining x4 doesn't have any x3s in it. And for the non-free variables, right, the coefficients or the entries that show up here are just coming from these two entries, or these two coefficients here, so minus 1 and 1. And then a corresponding thing for the other free variable, x4. So minus 3 and 1. And then, of course, for x3, there aren't any x4s, and for x4, we need a 1. Okay, so. All right, so, but if you think about it, there wasn't anything special about this particular reduced row echelon form that made this happen. If you have any reduced row echelon form, writing down the vector vector solution is going to look pretty much, or the parametrized vector solution is going to look pretty much the same. You write out the equations, move the free terms to the right, and then translate back to vectors. So really, we can kind of cut out the middleman here, because all we need to do is take our for the equations that have pivots in them, remember these leading ones, these are pivots, and these correspond to non-free variables. For rows with pivots, take those entries in our augmented column. Those go in a vector on their own. Free variables get zeros in this term. And then for each free variable, or for each non-pivot column, which corresponds to a free variable, we get that free variable times the negative of the entries from that column. That's for the non-free variables. For the free variables, you get a 1 corresponding to the free variable for the term you're on, and a 0 for all the other free variables. And then same thing here, right? These two entries are coming from here, except they're negatives because we had to move them over. And then here we get a 0 because x4 is not x3, and here we get a 1 because x4 is x4. So what this means, the upshot of all of this, is that we can jump directly from having a reduced row echelon form to writing down the vector parametrized collection of solutions for the corresponding system. And that's really nice. That cuts out a lot of writing. You know, conceptually it's not really changing very much, but it is saving us a lot of work, just writing all this stuff out. So just to see another example of what this looks like, suppose that we had this system of equations. I wrote some code to automatically generate this, and I need to change it so that it starts at 1 instead of 0, I guess. If you write down the augmented matrix for this system of equations and then do row reduction, this is what you get. I won't drag you through me actually computing this. But now that we have this reduced row echelon form, let's go ahead and write down the parametrized solution set. So because we have, so this is our augmented column over here. So we have five columns to the left of that. So that means there are 5 variables, and sure enough, x0 through x4, that's 5 variables. So when we write down our parametrized solution set, we have our 5 variables like this. So first, let's do our vector of constants. Now remember, for non-free variables, the entry in this constant vector comes from the right-hand side after row reduction, the augmented column. So that's for x0, x1, and x3. Or sorry, x2. That's not right. Sorry. x0, x2, and x3. There we go. So we need a -2 here, and a 0 here, and a 1 there. Okay, and then for the free variables, which are x1 and x4, those get zeros. Free variables always get zeros in this constant vector. Okay, now we get a term for every free variable. So x1 is a free variable. And then for the non-free variables, that's x1 and x4, the free variable corresponding to this entry gets a 1, and other free variables get a 0. And then the coefficients for the rest of these are the negatives of these guys. So a -2 here, and then a 0 here and here. And then our other free variable is x4. So for the x1 entry, we get a 0. For the x4 entry, we get a 1. And then the other entries are determined by the negatives of these. So 3, 1, and 3. There we go. So here is our vector parametrized collection of solutions where x1 and x4 are free. Of course, this doesn't change anything conceptually. So, you know, if you don't like just having more things to remember, you don't need to don't need to remember this process, but it is kind of nice because it saves us writing down all of this stuff, right? So it is a nice labor-saving device to get at the vector parametrized solution set. And just to foreshadow a little bit, we usually will be wanting the vector parametrized solution set.